All right, so before we start talking about bonding, we want to talk about Lewis dot structures, and then eventually we're going to move into bonding. We're going to go into Lewis diagrams, and so basically it's going to be a model of bonding. So we're aware that this is not exactly how the elements and electrons react, but it's a model of it, and this model is actually very simple. And the great thing about it is even though it's so simple, it has amazing predictive power. Right, so it's not perfect, but for how easy it is to do, it has really good predictive power. You're going to be able to predict the structure and the properties of all kinds of molecules using this Lewis dot structures and eventually Lewis structures. So what we're talking about here when we're forming bonds, we're talking about electrons. And remember our last discussion, core electrons are really hard to remove. And so we pretty much don't concern ourselves with those. What we're worried about here is the outer electrons. Those are the ones that are easy to remove. And so we're going to say that only valence electrons, we'll say matter. Right, the core electrons, they're still there, but they're not really going to do anything. And so the first thing you have to know is how many valence electrons any element has. And for our discussion, we'll basically just be focused on group 1, 2, and then 13 through 18, so just the main group elements. So let's take a look at nitrogen. So if you look at nitrogen, it's going to have 5 valence electrons. So let's write that out. So it goes 1s2, 2s2, 2p3, right? There's both equal 2 here, so there's 5 valence electrons. So let's go ahead and draw the Lewis dot structure for nitrogen. So what you do is you put the little symbol, an N for nitrogen, and then you draw little dots. The little dots represent the valence electrons. So there's 5 valence electrons, and so we add 5 dots. There's kind of 4 sides to this thing, right? There's always 4 sides, so we just put 1 dot here, and then we put them by themselves before we pair them up. So there's 2, 3, 4, and then once we put 4, we start pairing up, so the 5th one gets paired up, right? So we've got 5 dots for the 5 valence electrons. There's kind of 4 sides, right? Top, right, left, and bottom. And so we put 1 on each side, then double up. So you can think about what the Lewis dot structure for all of these main group elements would be, and they'd essentially be the same going down the column. Each column would pretty much be the same because it's got the same amount of valence electrons, just the symbol would be different. So let's just do this kind of first row. Lithium has 1 valence electron, so just 1 dot. Beryllium has 2 valence electrons, so 2 dots. Boron, 3 valence electrons, 3 dots. Carbon, 4 valence electrons, 4 dots. Nitrogen, 5 valence electrons, so 5 dots. Oxygen, 6 valence electrons, so 6 dots. Fluorine, 7 valence electrons, so 7 dots. And then neon, 8 valence electrons, so 8 dots. And then there's your Lewis dot structure for all of these. And so just some things to keep in mind is that filled valence shells are energetically favorable. So just like the ball wants to roll down the hill, our elements generally want a filled valence shell. And so when you're thinking about filled valence shell, you're thinking about 8 electrons, right? 1, 2, 3, 4, 5, 6, 7, 8. So 8 valence electrons, and later on we'll learn this as the Octet Rule. It's not really more a rule, it's more of kind of just a guideline. The obvious exception here is that hydrogen and helium only want 2 electrons. We call that a duet because there's 2 of them. Another thing you have to realize is like lithium has 1 valence electron. So if it loses 1 electron, it has a filled valence shell. In this case, just 2 electrons. Same thing, sodium. If sodium loses an electron to become Na+, it has a filled valence shell, this time an octet. So filled valence shells, energetically favorable